Good morning, good afternoon, or good evening from your side. I am Rahul Maharaj, and I will be teaching grade 12 physical science, and I will be covering work, energy, and power. So let's get started. So here we have work and energy. So here we have this block. We apply a force F, and the block moves a displacement delta x. So what is work? Well, the mathematical definition of work is the product of the force that's acting on an object times the displacement. It's the product of the force being applied and the displacement. And it's defined by this equation. W is equal to F delta x cos theta, where F is the applied force acting on the body, delta x is the displacement that the body undergoes, and theta is the angle between F and delta x. Okay, so work is the energy that's being transferred to a body. For example, you push your book some distance, you are applying energy for that book to move from point A to point B. So let's look at our first example. The work done by a force in the direction of the displacement. Calculate the work done in moving a box 5 meters with a force of 10 newtons at an angle of 30 degrees. Give this problem a try using the formula. So here we have our solution. So W is equal to F delta x cos theta. F is 10 newtons and delta x is 5 meters. And theta is 30 degrees. So substitute that and you will get 43.3 joules. Let's look at our next example, which is the work done by a force that is opposite in direction to the displacement. So now the force is opposite in direction to the displacement. So here's our example. A truck breaks 20 meters on a gravel bed. Calculate the work done given that the magnitude of the frictional force exerted on the gravel bed by the tires is 25 newtons. Pause the video and work this example. So here's our solution. The frictional force is opposite in direction to the motion of the truck. In other words, the displacement of the truck. The frictional force is opposite in direction to the displacement of the truck. And the angle between the frictional force and the displacement is therefore 180 degrees. Okay? The work done is given by W is equal to F delta x cos theta, where F is 25 and delta x is 20 and theta is 180 degrees. So perform that substitution and we will get 500 joules. Now you may ask the question, where does the minus sign comes from? The minus sign is because negative work is being done, since the frictional force and the displacement are in opposite directions. And negative work means that the truck is giving 500 joules of energy to the gravel bed. So like I said, negative work is being done by the frictional force of the tires to the gravel bed, and the truck's tires will transfer 500 joules of energy to the gravel bed. Now let's look at another example where work is done by a force that's perpendicular to the displacement. I'll give you a few minutes to think about what the work will be if you have the force and the displacement being perpendicular to each other. So pause the video and take a minute to think about that. The work that is done by a force that is perpendicular to the displacement is 0. Why? Because cos 90 degrees is 0. And forces like the normal force that's exerted by the surface on this body, or the magnetic force experienced by a charge in a magnetic field, the work done is zero. Now let's look at net work being done. So far, we only found the work done due to one force, but nature doesn't only allow one force to act in a body. And you saw this a lot in grade 11. So suppose you have n number of forces, F1, F2, and Fn acting on this body. So then the net force is going to be the superposition of these n forces, F1 plus F2 plus Fn, okay? And the net work done is given by W net is equal to F net delta x times cos theta. And if we substitute our F net, we get this expression, F1 plus F2 plus all the way to Fn times delta x times cos theta. And if we distribute the delta x cos theta inside the brackets, we will get this expression where we have F1 delta x cos theta plus F2 delta x cos theta plus Fn delta x cos theta. And this is equal to W1 plus W2 all the way to Wn using this formula. Now let's look at an example where the work is done by many forces that's acting on a body. Consider a 100 kg crate that is sliding 2.5 meters down a rough inclined plane, which makes an angle of 25 degrees with respect to the horizontal. The rough inclined plane has a coefficient of kinetic friction of 0.25. Calculate the work done as a result of the crate sliding. So here we have our diagram where we have this 100 kg crate that's sliding down on this incline that makes 25 degrees with respect to the normal. And I also have a free body diagram where you have the weight of the crate acting vertically downwards. And if you resolve the weight into perpendicular and parallel components, you'll find that the parallel component is responsible for the sliding. And since it's on a rough inclined plane, there's friction. And the surface exerts a perpendicular force called the normal force that's equal in magnitude to the normal component of the crate, but opposite in direction. You guys have done this extensively in grade 11. So if you forgot, please go back and revise. That's the free body diagram that I drew. Now let's look at the solution here. The net force acting on the sliding crates is given by F is equal to the component of the weight that's parallel minus the frictional force. The component of the weight that's parallel is equal to mg sine theta as we saw in the free body diagram. And F is equal to mu k times n, where n is the normal force and mu k is the coefficient of kinetic friction, as you've seen in grade 11. And n is equal to the perpendicular component of the weight on the incline, which is mg cos theta. We have mg sine theta. We have mu k mg cos theta. We see that mg is common in both terms, so we factor that one out. So mg into sine theta minus mu k cos theta. We perform our substitution where m is 100, g is 9.8, times the sine of theta, which is 25 degrees, minus mu k, which is 0.25, cos of 25 degrees, and you will get an answer of 310.62 newtons in the direction of motion. Now, since the net force is in the direction of motion, the angle between the net force and the displacement is zero, and that implies that positive work is being done on the crate. And if the work being done on the crate is positive, that means that the crate is gaining energy. And so the net work is W net is equal to F net times delta x cos theta. We found what F net is. It's 310.62. Delta x is 2.5. And theta is 0 degrees. Plugging that all in your calculator, you'll get 776.56 joules. So 776.56 joules is being gained. So the crate gains 776.56 joules when sliding down this rough inclined plane. Now let's look at gravitational potential energy. Okay, so say you have this box of mass m that has a weight mg, and if, let's say, you try to pick it up, a displacement delta x. So let's say you you pick this box up, a displacement delta x. The question is, what work is being done? Okay. So suppose a body of mass m is doing work against the gravitational force field from a position, let's say, y1 to a second position, y2. So here you have this position being y1 and the second position being y2. So it undergoes a displacement from y1 to y2. You pick it up from y1 to y2. What work is being done? So the work being done is given by W is equal to minus mg, y2 minus y1. The minus sign comes from the fact that the weight and the displacement, they're both in opposite directions. So theta is equal to 180 degrees. And so negative work is being done, which can also be written as minus mg delta y. And we find that the gravitational potential energy is the work done against the gravitational field. So gravitational potential energy is the energy that a body has due to its position in the gravitational field. And it's defined as U is equal to mgh, where m is the mass of the body, U is the gravitational potential energy, g is the gravitational acceleration, and h is the height. Okay. Okay, let me just clear all these drawings. So let's look at an example here. Calculate the gravitational potential energy of a 1,200 kilogram elevator that's doing work against the Earth's gravitational field as it goes from ground level to the second floor, which is 10.5 meters. Attempt the question and then play the video to see your answer. So let's look at the solution here. So U is equal to m times g times h, which is equal to 1,200 times 9.8 times 10.5. Plug that in your calculator and you'll find that 123,480 joules of work is being done against the gravitational field for the 1,200 kg elevator to go from the ground floor to the second floor. Now let's look at kinetic energy. Kinetic energy is the energy that a body has as it's moving, and it's given by the formula K is equal to half m times v squared, where K is the kinetic energy, v is the speed of the moving body, and m is the mass of this body. So in chemistry, you would have also picked up that the temperature of a gas is the measure of the average kinetic energy of all the gas molecules. And the kinetic energy of the body is important because it can help us, calculate the work being done to or by an object and what's the force that causes this change in kinetic energy. And this is as a result of the work energy theorem. So let's look at an example before we go to the work energy theorem. Calculate the kinetic energy of a 100 kg wrestler charging at 7.5 meters per second towards her opponent. Okay. So pause this video and attempt the question. So the mass of the wrestler is 100 kgs. That's your M. Your V is 7.5. All you need to do is calculate your K. So here's our solution. K is equal to half mv squared. Do your substitution where you have half times 100 times 7.5 squared, and you get an answer of 2,812.5 joules. So the wrestler weighing 100 kilograms will gain 2,812.5 joules of energy as she charges towards her opponent at 7.5 meters per second. Now let's look at the work energy theorem. So suppose a body is moving from an initial velocity u to a final velocity v along a displacement delta x. We use the kinetic energy to represent that, where you have v squared equals u squared plus 2a delta x. That's our equation 1. And what we can do is we can multiply both sides of equation 1 by mass m. Doing that, we have mv squared equals mu squared plus 2ma delta x. That's equation 2. Then we divide both sides of equation 2 by 2, and that gives us half mv squared equals to half mu squared plus ma delta x. That's equation 3. And what we can also do now is we can take the half mu squared to the other side, and it becomes minus, as in equation 4. So you have half mv squared minus half mu squared equals to ma delta x. But hang on, we also know something. We know two equations. One is k is equal to half mv squared, and the other is Newton's second law, which is F net's equal to ma. And if you plug in those definitions, your equation 4 will become equation 5, which is the equation for the work energy theorem. Okay. Okay, so 5 is the work energy theorem. Now let's look at an example here. But before we do that, let's state the work energy theorem, which states that the total work done to or by a system is equal to the change in that system's kinetic energy. So if you push a book a certain displacement and its kinetic energy changes from 0 to some non-zero kinetic energy, that change in kinetic energy will be equal to the work that was done to that book in order to move it from one point to another. So let's look at an example. A 5-kilogram body from velocity of 13 meters per second to 25 meters per second goes through a displacement of 10 meters. Let's calculate the net work done on the body, and then we calculate the force acting on the body. So here's our solution. W net is equal to delta K, which is the work energy theorem, which is equal to half mv squared minus half mu squared. You substitute, you'll have half into 5 times 25 squared minus half times 5 times 13 squared, and that will give us 1,140 joules of energy that's gained as this body accelerates. Next, we calculate the force. So W net is equal to F net times delta X. We have our W net as 1,140. We have our delta X as 10. So all we need to do is divide both sides by 10 to get F net. And so F net is equal to 114 newtons in the direction of motion. Now, I made this question up, but it seems like a good question to put in exams. So a car accelerates down an incline from a speed of 10 meters per second to 25 meters per second. The inclined plane makes an angle of 30 degrees with the horizontal, and the coefficient of kinetic friction is mu k is equal to 0.45. Calculate the displacement that the car travels up the inclined plane. So I urge you guys to take at least 7 minutes attempting that question and then check your solution. Okay? So here's the solution here. We first draw a free body diagram. So in the free body diagram, we have the weights acting vertically downwards. We have the sliding force, which is the parallel component of the weights. We have the normal force, which is equal in magnitude to the perpendicular component of the weight. Since it's a rough incline, there's going to be frictional force. Okay. So now we have the diagram that will help us calculate the net force. So from the work energy theorem, F net times delta x equals to delta k. The net force is mg sine theta minus mu kn times delta x equals to half mv squared minus half mu squared. N is equal to mg cos theta. But on the left-hand side, we see that mg is common, both terms. So what we can do is we can factor mg out. So we have mg times sine theta minus mu k cos theta times delta x equals to half m v squared minus u squared. I just factored out the m on the right-hand side. But now let's see what happens. We see that the m's cancel out, and that makes us happy. So we have g sine theta minus mu k cos theta times delta x equals to half v squared minus u squared. Now we can do our substitution where we have g being 9.8, we have theta being 30, we have mu k being 0.45, we have v being 25, we have u being 10. So we then simplify to get 1.08 delta x equals to 262.5. And we divide both sides by 1.08, and we'll just get delta x being 242.87 meters down the inclined plane. Now we look at power. And what is power? Power is the rate of change of energy. In other words, it's just the work done per unit time by a body or to a body. So P is equal to W divided by delta T, where P is the power, W is the energy, and delta T is the change in time. Work is energy. Like I said, if you push a book from one point to another, or push or roll a ball from one point to another, work is being done to those two things, and as a result, energy is being gained, as we saw in our calculations. So P is equal to F delta x cos theta. I just use the definition for work. All right. And also recall that V is equal to delta x divided by delta T. But before we go any further, I just wanted to say that the power is delta W over delta T. Okay. So there's a typo here. So I should have put a delta here, and here we have a delta. All right. And if you have your force being constant, you could write it as F divided by delta T. So sorry about that. Just got a little bit confused there. So power is the rate of change of energy. So because you have V is equal to delta X by delta T, you can substitute that into P, and you'll get P is equal to FV cos theta, right? Now let's look at an example here. Calculate the power that a 10 Newton force exerts on a block to move it 2.5 meters in 2 seconds. So give yourself some time to work that out. So here's the solution here. The angle between F and the displacement, delta X, is 0 because these vectors are in the same direction. And because of that, cos 0 degrees is equal to 1. So positive work is being done. So P is equal to F delta X by delta T. I forgot about the cos theta because I didn't forget about that. I just said that because we have cos 0 here and cos 0 is 1, that's why I didn't put the cos theta there. So P is equal to F delta X by delta T. Make your substitution, 10 times 2.5 over 2, and you will get P being 12.5 watts. So the SI unit for power is watts. So this is all I have to say on work, energy, and power. I hope you've enjoyed my presentation. Please let me know. Please, if you have any questions, please send me question on the comment section, and I'll try to answer them. Thank you so much, and bye.